Deep in the Peruvian Amazon, thermal imaging satellites detect a massive heat signature. It's a river, 4 miles long, running at temperatures approaching 100 degrees. Looking at the expansive, flat canopy from above, the landscape appears completely ordinary. There are no obvious tectonic fissures or craters, but heating a river of this volume to boiling requires a massive, continuous thermal engine. In traditional geoscience, a sustained heat source of that magnitude on the surface requires magma. Finding this level of thermal energy output in the middle of a quiet, stable sedimentary basin violates the standard rules of surface hydrology. Local indigenous accounts of Shane Timpishka provided the first empirical records of this anomaly, describing a river that boils through the power of a serpent spirit. For decades, the global scientific community dismissed these accounts as physical impossibilities. Geologists reasoned that local storytelling had exaggerated the presence of a few standard warm springs. The skepticism was rooted in structural logic. To get a boiling river, scientists expected to see the active volcanic markers and magma plumes common in the Andes. None of that architecture exists in the Amazon basin. Treating the indigenous accounts as accurate empirical observations, researchers had to discard the magma requirement entirely. The heat had to be generated by a purely structural, non-volcanic mechanism. A close inspection of the river confirms the extreme temperatures. The water is hot enough to instantly neutralize local wildlife that falls in, maintaining lethal, near-boiling thresholds consistently along its path. This map shows the major tectonic activity in the region. While the Andes to the west are highly active, the Amazon basin sits on a geologically quiet sedimentary layer with a confirmed absence of magma plumes. Without magma, we have to look at the geothermal gradient. This graph plots the natural rate at which ambient rock temperature increases the deeper you travel into the Earth's crust. The temperature increases roughly 25 degrees Celsius for every kilometer you go down. To reach near boiling temperatures through ambient crustal heat alone, surface water must travel incredibly deep. The heat itself is normal. The actual anomaly is the existence of a subterranean fluid pathway, capable of routing surface water deep into the crust and back up again. This massive hydrological loop begins with meteoric water. Rainfall enters the ground in a completely different location, far from the visible thermal anomaly. For this to work, the catchment area requires a specific geology, vast sections of highly permeable sedimentary rock that can absorb millions of gallons of rainwater like a massive sponge. Once absorbed, the water travels downward through a network of continuous tectonic fault lines. These deep-rooted fractures provide the plumbing necessary for the water to sink further into the earth. This cross-section shows the descent trajectory. Following the geothermal gradient, this water must sink to a depth of nearly 3 kilometers to reach the 100-degree mark. At 3 kilometers down, the conditions are extreme. The immense pressure from the rock and the water above it compresses the superheated fluid, preventing it from flashing into steam. Gravity and deep faults successfully generate a massive subterranean reservoir of superheat as liquid. But that trapped thermal energy is completely inert unless a highly specific geological trigger forces it back to the surface. The primary thermodynamic problem here is heat retention. Ascending water will naturally cool down by transferring its thermal energy into the surrounding colder rock as it rises. To maintain its temperature, the boiling river requires an express lane. It relies on a perfectly vertical, high permeability fault conduit that shoots the water straight up. This model shows the resulting U-tube effect. The massive weight of the cold water continuously descending in the catchment area generates immense hydrostatic pressure, which acts like a piston to force the deep, hot water upward. The resulting upthrust happens at an incredibly high velocity. The superheated fluid moves so quickly that it outpaces the rate of thermal transfer, preventing the surrounding rock from cooling it down. This highly pressurized, superheated fluid finally hits a breach point. It violently intersects with the surface sedimentary layer in the Amazon, spilling out to form the river. The boiling river operates as a rare thermodynamic exhaust valve. It only exists because of a perfect geometric alignment, deep descent, continuous geothermal heating, and rapid, pressurized vertical ascent. Peeling back the Amazonian surface reveals a continuous hydrothermal loop extending kilometers into the crust, operating as a single, massive engine. This complete geological model forces us to reevaluate the original accounts of Shenandoah. The local stories detailing a river heated from below were completely accurate. They served as precise, empirical observations of a high-efficiency geological engine operating kilometers beneath the jungle floor. This purely structural, non-volcanic model requires geoscientists to update their calculations. It proves that significant hydrothermal potential can exist in stable, quiet tectonic zones worldwide, provided the fault geometry is correct. The mechanics of the boiling river provide a new blueprint for identifying similar anomalies in other geologically quiet regions across the globe. Subscribe to Insight Engine for more.